So now I want to talk about another inverse form, okay? I want to say, well, what about if we have x equals the inverse, y equals the inverse sine of x, or inverse tangent of x. Started this video strong. Inverse tangent of x. Now, what does that mean? Well, what it means is we can take tangent of each side, and we're left with the tangent of y equals x. Again, next thing I'm going to do is I'm going to draw a triangle that illustrates that for me. The tangent of y equals x. Well, what's x? Well, the tangent of y should be opposite over adjacent. So in this case, I would have to say, well, then this is x and this is 1. How do I know that? Well, because the ratio of opposite to adjacent has to be x. And if I have that, instead of using c squared minus b squared here, I am going back to the basic Pythagorean theorem and saying, well, then this side is a squared plus b squared. Well, that's 1 plus x squared would be the hypotenuse, square root. So now I've got my triangle drawn. I'm going to take the derivative of this, keeping in mind that what I ultimately want to find is I want to find dy dx. So derivative of tangent, well, secant squared y, and then because of the chain rule, dy dx, derivative of x, still 1, because I'm taking the derivative with respect to x of the whole thing. So I say secant squared y, well, what I want is dy dx by itself. That means I'm going to divide each side by secant squared, which leaves me that. Of course, secant squared is 1 over cosine, which means cosine is 1 over secant. So this turns out to be just cosine squared. And then again, I look to my triangle and I say, well, cosine squared, cosine has to do with this guy and this guy, right? Adjacent and the hypotenuse. So 1 squared is 1. And this whole thing squared gets rid of the square root. So it's like that. So again, that's what the derivative of inverse tangent gives me. So I come back over and think about, well, what does that do in terms of a derivative, or in terms of an integral? It means if I have something of this form, du over, and again, there doesn't have to be a 1 there, it could be any constant. So I'll say a squared plus u squared. If I have that case, then that is inverse tangent. And just like here, if this is not 1, we end up with a ratio of u over a. And in the case of tangent, we also get a 1 over a that occurs out front. It just gets there because of the chain rule and various other things. Okay? So again, let me put up here an example. If I had the following, if I had the integral of, let's say 4 dx over 9 plus 4x squared. Now, that doesn't exactly fit this form, but I look at this and say, is that something squared? Yes. Is that something squared? Yes. And by the way, this could be 7. 7 is still something squared. It's radical 7 squared, okay? But it's cleaner if we do it this way. If we look at this and we say, okay, I need to make some substitutions in order to use this formula. I think it's that formula. Why do I think that? I don't see a square root. If I saw a square root, I might look for something like this. But I don't see a square root. And I see a sum in the denominator. All right, so I say, I wish that it said u squared. It doesn't. It says 4x squared. I wish that it said a squared. It doesn't. It says 9. But that enables me to say, well, then u is 2x and a is 3. Moreover, it allows me to say du dx is 2, which allows me to rearrange that and say dx is du over 2. Then I come back here and I say, okay, we'll make that substitution. I've got a 4. That's just a number. That's 4. dx is du over 2. In the denominator, that is a squared, 3 squared. That is u squared. U is 2x. I say, now that, see, this is going to cancel, and that's going to leave me with a 2. But of course, that 2 can just come outside the integral sign here. And I have 2 over, or 2 times the integral of du, 3 squared plus u squared. And my formula over here says that I go 1 over a, it's an inverse tangent. I've got this 2. I then have 1 over a, which in this case is 3. I have the inverse tangent of u over a, which is u over 3. But we know u is 2x, so we come back in here and say 2x over 3. Okay? So that's how inverse tangent works. Now, it turns out that if I was to do the same analysis with inverse cotangent, in the same way that cosine only differed by inverse sine by a negative sign, inverse cotangent would only differ from inverse tangent by just a negative sign. And I'm not going to do it this time. I'm not going to go through that again and show you it doesn't help us to do that. You just know if there was a negative sign here, you're pulling it out anyway, and then you're looking for inverse tangent.